So again, we're going to talk about correlation relationship between two variables. We're going to call one of them X, one of them Y. X is called the independent variable because X is, or we call it from the word explain. X explains the Y. X explains the second variable, which is the dependent variable. We're going to call it Y, or we're going to call it response. So just to give you an example of two things, or many examples of those things, here's three examples. Example 1, example 2, and example 3. Now, in example 1, we know and we suspect there is a relationship between cost of a college and the number of students enrolled. Now, the cost in this case is expressed by variable X, and the number of students is expressed by the number of the variable Y. Do you think there is a relationship between the cost of college and the number of students? In other words, do you think that the cheaper the college, the more students will go to? The more expensive the college, the less students will attend? What do you think? Is there a relationship between cost and number of students?
Yes.
Okay, what about the rest of you? I'm sorry, some people are typing, and I mentioned earlier that typing, I don't see that because I'm covering half the screen right now. So, but okay. Yeah, thank you. So I'm going to cover even your names in here because we don't want to be able to, or others to be able to see that because it's recorded. So yes, we think there is a relationship between costs and the number of students. For example, if your college decides tomorrow to make the tuition $1,000 a credit hour, so if you're taking 15 hours, it's going to cost you $15,000. How many students will afford to go there? Okay. Now the second thing example we look at the speed of the car and the amount of the ticket. So the speed of the car and the amount of the ticket. We know that the faster you go, the higher the ticket. So if you are within 5 miles, you get a ticket. If you are between 5 to 10, it's a ticket is going to go to higher and higher and higher, and so on. So yes, there is a relationship between speed of a car and amount of the ticket. Also, there is a relationship between the size of the home that you like to buy and the price of the home. You are told, and we are told all the time, listen, if you want a big home, you have to pay more money. So there is a relationship in here. And notice that in this case, we talk about why. Why always a response. Like if you look at the home, and let's look at the third example. Look at the home, and they tell you the home is 300,000. I say, how come 300,000? They tell you because it is maybe 2,000 square feet home. It's a big home. If you want to pay less, go look for a smaller home. So that the reason in here is that the X explains the Y. The X, in this case, the size of the home, will determine the price of the home. So those are three examples of relationships, and in statistics, we don't call them relationships. We're going to call them correlation. So we're going to use the name correlation instead of a relationship. Now, like any points, like anything in here, I think my cat wanna go outside. Like anything else in here, when we come up with X and Y, we come up with a graph. So if I give you a list of X's and Y's and I tell you graph them, you can come up with a graph. Now that graph in here, we're gonna call that scatter plot. So a scatter plot is the plot or the graph that we get when we graph the X's and Y's in our problem. So for example, in here, let me just go in here and just show you an example. For example, let's say that you have a table in here of X's and Y's, 0, 1, 2, 2, 3, -1, 1, 2, and 2, 5. Let's say that we have those points. Okay. Now let's assume that those are the days in, or forget the days. Let's say that you were fishing, and 0 is not going to work in here, so we are fishing. Let's say like you are fishing and you caught fish, and where X is the length of the fish. So X represents L, length, and the Y represents the weight, W. Now, this cannot be native, so because weight cannot be native, so let's say it is equal to, let's say 4. So you went in there and you caught the first fish and you measured the length of the fish. Then after that, you weighed the fish and the second one and the third one, the fourth one, the fifth one. It is, if you try to graph them, and in here, you notice that as we graph anything else as we did in the past, when it's 4, it's 1, here is 4, 1. Then it's 2, it's 2, here is 2, 2. Then 3, 4, here is 3 and 4 somewhere in there, so here. Then 1, 2, here is 1 and here is 2. And 2, 5, here is 2 and another 5. So now when you look at those points graphed in here, that is called a scatter plot. So this is what we mean by a scatter plot. A scatter plot is when you graph the points. Now we're going to show you with the StatCrunch. With technology, we can do scatter plots very fast. We don't have to really do it by hand. And our goal in this class, our goal is to come up with a relationship that is called linear. Now, we're not looking for perfect linear. We're looking for something close to be linear. So if I go back to my problem here, this is not close to be linear. But if I have another one like this, where I have dots in here like this. Now, if you look at those dots in here, they are very close to be linear. Because if I put an imaginary line in there, they line up around the line. So this is not really perfect linear, but it's close enough. So we're going to talk about those things later on. So next, we're going to talk about some examples. And again, look at those examples. We're not looking for perfect. We're looking for close enough. Like if I look at the first one and I try to put an imaginary line through, it seems like the dots are lined up around this line. But the dots are going down. As we go to the right, the line is going down. That's the reason why we're going to call that a native linear correlation. Because, again, it's native because it's coming down. And the second thing is linear because it's close to be linear. It is not perfect linear. So that's the reason why we have that. Now, if you look at the second line, and if I put an imaginary line through, the dots are lined up around the line, and it is going up. So that is the reason positive, and it is linear because it's almost linear. It's not perfect linear. Now, if you look at number, again, let's call this one graph 1, and this is graph 2. This is graph 3, and this is graph 4. If you look at graph 3, I cannot really put a line to represent the points. Because the line can be this way or this way or this way, I cannot tell. In this case, we say there is no correlation. In this case, there is no relationship in here. I cannot tell if the point's going up or going down or going sideways. I cannot tell. That's the reason why we call this no correlation. Now, if you look at the graph 4, it seems like the dots are going up, but then the dots are going down. So this is not linear because linear means it either goes up or goes down, but not both. In this case, we say there is no linear correlation here. So it is not linear, okay? And in this case, by the way, it is curved. So this is, if you continue with statistics beyond this class, we call that quadratic correlation. We're not going to study this type of correlation in this class. So when we see something like that, we say there is no linear correlation, nonlinear correlation. So in this case we don't like, and this case we don't like, because we only look for the cases where we see something close to be linear correlation. Any questions? Okay. Now, this is just an example. And in this example, it talks about there is an economist here, and it's trying to trying to see if there is a linear relationship between two things: the country's gross domestic product, which is GDP, in other words, the country's wealth, and carbon dioxide, CO2 emission, in other words, pollution. Do you think there is a relationship between wealth and pollution? Now, many of us may assume yes, some may assume no. So we go and do a study. So this economists collected data from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 countries. And notice that the wealthiest country is this country. And if you look at the pollution, the highest number is this. Now, the second wealthiest country is what? Can you tell me which one is the second wealthiest? Again, look under the GDP and tell me which is the highest number.
3.9.
3.9. And look at the pollution. It seems like the pollution is also the second, yes or no? So it seems like, and if you look at countries that on the lower scale, like this one, let me change the color of my marker. If I'm looking at a country like this one, which is 0.9, which is not as wealthy, and notice that the pollution is low, okay, compared to the other ones. So it seems like the wealthier, the more pollution. And this is common sense, because what makes countries wealthy is mainly is their manufacturing, okay, and how good and how big their manufacturing background is. And remember, with manufacturing comes pollution. Some may claim that it's cars. Yeah, cars cause pollution, but it's not as much as manufacturing. But it's still, in a wealthier country, people can afford cars, and in a poor country, people cannot afford cars. So this goes along. So you notice that there is a correlation. But again, we cannot just decide based on that. We need to go in there and see if there is a linear correlation. So what I do in here, I go and I build what I call the scatter plot. So if I go and build a scatter plot, okay, the scatter plot is going to look like this one. Now, if I try to fit a straight line within this scatter plot, the line is going to be probably like this. Because notice that as we go to the right, as the wealth goes up, the pollution goes up too. And notice that there is a straight line in there. Because if you try to do this, if somebody tries to go like this, we say the straight line is not really fitting the points. So you have to find a line that just chases the points somewhere in between. Okay, where some points above the line, some points under the line, and this is the line. If you look at this line now, we see that this line really is going up. That's the reason why we call that positive. And it's also fits something called a linear correlation, because I can come up, linear means I can come up with a line, you know, that guides me or takes me through the journey of that scatter plot. So in this case, it seems like there is a positive linear correlation. Notice that this positive linear correlation is not perfect, because it will be perfect if the dots appear like this, like here one, here's one, here again, here's one, here's one, here's one. Like if all of those dots are on a straight line, but they are not really straight line, but the dots, we see the dots, some above, some under. So this is still, it's a positive, but it's not perfect positive. And we're going to talk later on about those things. We're going to talk about what makes a correlation positive correlation, what makes a correlation less than positive correlation. Here's another example. In this example, it talks about two things. Do you think, and I can ask you this question, do you think there is a relationship between the hours of exercise and GPA? Do you think people who work out a lot tend to do better than people who don't work out a lot? Because we see this all the time. There is people who think there is a relationship between, and a strong relationship between, sports and GPA. And I'm sure when you were in high school, and some of you still in high school, the high school always, and the administrators in high schools always try to promote sports as a way to achieve good grades. And they always brag about those things. So do you think that, remember, when you talk about sports, we talk about exercise. So do you think there is a relationship between exercise and GPA? Like the more you work out, the more the exercise you do, the higher GPA you get? Now, we can answer the question, say, some of us may say yes, some of us may say no. It depends on your background and how you believe in those things. But we can come up with a relationship through StatCrunch or through statistics in general. We can go and draw for this data a scatter plot. And if we do a scatter plot, look at this. Here's our scatter plot. Our scatter plot, if I try to put a line, I cannot really put a line like this, because then most of the points are under. I cannot put a line like this because this is not, because again there is a cluster here and cluster there. So the line release, somehow if I want to put the line has to be go flat. And no, go flat, this means no correlation here. Okay? So because again it's going to be either positive, negative, or nothing. Okay, so in this case, it appears to us that there is no correlation in here between the hours of exercise and the grade we get in high school or GPA. Okay, and we can look at this further down the road. Now, so I'm going to stop here for a second and just focus on this concept. If you want to see if there is a relationship or a correlation between two variables, one way to do that is through a scatter plot. Now, you can do a scatter plot to see if there is a relationship, but there is another way in statistics to see if there is a relationship between two things, which is what we call the coefficient of correlation. The coefficient of correlation, and we call that R. Remember, if we are dealing with a sample, we call the coefficient of correlation R. If we are dealing with a population, we call that rho, R-H-O. Okay? So there are two ways, and let me just clear this in here. This is the rho here. It's called rho for a population. Now, in real life, sometimes we can survey the whole population. So if I collect data about everything in the population, for example, if somebody tells you, listen, I want you to see if there is a relationship between the number of years of experience and the salary of the faculty at your high school. Now, in your high school, how many faculty members in there? Let's say there is 50. So it is possible to get to all of them and look at their records, how many years they work and whatever, and how much they make. It's public record probably. So you can come up with the coefficient. We call it R. No, I'm sorry, you call it rho, because you get to all of them. Now, but what if you're talking about is there a relationship between the years of experience and the salary of all school teachers in Ohio? It is very impossible to get to all of them, and that's the reason why we rely on a sample, and when we do calculations, we get R, small r. And in real life, we rely more on R than rho because rho is impossible. So remember the two, but there is something called the coefficient of correlation. I'm going to clear this and tell you, how do we calculate that coefficient of correlation? To calculate the coefficient of correlation, we have to use this lovely equation. But this is very time consuming and it's insane to do by hand. It's not really insane, but if we have like 5 pieces of data or pairs X's and Y's, it's easy. But in real life, we may have hundreds of those X's and Y's. And as a result, it becomes so hard to do. That's the reason why we're going to rely on technology. And when we rely on technology in here, we talk about how to use StatCrunch, because this is the technology we use in this class. So how do we use StatCrunch to calculate R? How do we find R? Actually, I said you can find R and more, because whatever you're going to do to find R is going to give you lots of other things. So to do that, the first thing you need to do is you need to copy your data into StatCrunch. Now, there is a way to copy your data into StatCrunch. If you are doing homework, just hit on the icon next to the table, copy into StatCrunch is going there very fast. But if you want to do it by hand, you have to be careful. You have to put the independent variable. In other words, you have to put X under variable 1. And you have to put the dependent variable, which is the Y, under variable 2. Okay? Then after that, you're going to follow those commands. Now, if you follow those commands in here, that should give you the R, and it should give you everything else that we need, or not everything, but most of the things we need in this class. So let me show you this example we just mentioned here. This example about hours of study, or I'm sorry, hours of workout or exercise and GPA. I put this data already into StatCrunch because I don't want to take too much time doing that. So I put my data into StatCrunch, and let me go back to here to the instructions, and I'll show you side by side in here how we do this. Now, again, we're going to go, after you put the data into StatCrunch, you're going to follow those commands. Press the Stat key and go down to regression, and you're going to go to linear, simple linear regression. And the X variable will be the hours of study, and the Y variable will be the GPA. And we, again, look at this. We are trying to see if the hours of, hours of exercise, not study. The hours of exercise can influence the GPA, can make the GPA better or worse. So the GPA is dependent. That's the reason why we put the GPA into the Y and the X into the independent, in this case, which is the hours. Now, just put the X and Y as recommended, 1 and 2 here, and skip everything else in here and go down to compute. And when you come down to compute, you're going to get the R. You're looking for R, look at this list, and here where it says R. Notice that the R that we have, let me make this small now. The R we calculated in this example is native 0.16, let's say 4. Let's go 3 places. So the R is native 0.164. Now, so how are we going to benefit from R? We calculated R. How are we going to benefit from R? Let's go to the next slide and talk about this. Any questions before I continue?
No.
Anybody else?
No question.
Okay, so let me give you this example outside of statistics. Now, if you, and I always give this example, if you start your car in the morning or something, and the car is cranking in there and it takes a while for the car to start, you suspect there is something wrong with your battery. So you decide to go to a place like AutoZone, and they will hook the car to a machine. And if the pointer of the machine goes towards 0 in the middle, or like if the machine sometimes goes to the native or something, it's bad battery. Now, if it goes into the right direction, to the green, whatever it is, a good battery. We're going to talk about something similar here. It's not quite the same, but similar. There is a scale for R that goes from native 1 to 1. R cannot be less than native 1. R cannot be more than 1. Now, if R points to 0, if it's pointing to 0, then we think, if R is 0 or close to 0 in that neighborhood, then there is no correlation. And this is an example, of no correlation. Here's a picture, and you see dots like this. You can't tell if those dots are going up and down. Now, remember, if you have data like this one and calculate the R for the data, you're going to get some number very close to 0. It can be negative, can be positive, but within a small range around 0. If R is very close to 0, then there is no correlation. Now, what if R starts going away from the 0? Now, if R is going away from the 0, we start talking, let's say if R is in here, we talk about weak. Now, if it goes to here, we're going to talk about strong. Now, what if it's between weak and strong? We can say moderate. Now, when it goes, the closer it gets to 1, the stronger it gets. Same thing in here. If it's in here, we can say weak. No, remember, we can say weak, but we can say native weak. If it is in here, we can say moderate. If it's in here, we can say strong. And it's here stronger and stronger and stronger. If we hit the 1, it becomes perfect. Perfect like this picture. Perfect means like a straight line, exactly 100% straight line. Now, if it is native 1, it is a straight line, but is coming down, native. Now, if it's not 1 or native 1, the points is not going to form a straight line. They're going to be far away from the straight, a little bit far away from a straight line if it's strong, and more away from a straight line if it's weak. and far, far away from a straight line if it is no correlation. And we're going to see some examples. But this is how we look at it. 0 is no correlation. Go to the left of 0 or right of 0, and things gets better and better and better. Okay? Or in strength. And we call it weak, then moderate, then strong, then very strong, and so on. So this is how we look at data. Let me give you examples. And here we have 6 examples, actually. So let me label those as 1, 2, 3, 4, 5, and 6. Now let's look at number 1. Number 1, if you look at the dots are lined up in a straight fashion, 100% straight, and they are going up. So there is 2 things in here. Perfect because they line up, and positive because they go up. So we call it straight or perfect positive. And notice that R will be 1. Now look at the second graph. If I put a line, is going up, so it's positive. And the dots are not far away from the line, strong. And if you look at the R, it's close to 1. 0.81 is not far away from 1. Okay? Now look at the dots in the third graph. If I put this, it seems like the dots are going up. As we go to the right, the dots are going up. But notice that the dots are further away from the line than they are in 2. In other words, the further the points are from the line, the weaker it gets, but still it's going up, positive, but it's weak. And notice that the R is close to 0.45, half the way between 0 and 1. Now, if you look at number 4, the dots are perfect, but going down. So it's going to be perfect, native, and R is native 1. Now, if we look at 5, and if you put a straight line in there, my line is not straight anyhow, but if you put a straight line in there, the dots are very close to the straight line. They are not perfectly on the straight line, so it is strong and it's native. And look at R, is native 0.92. Native 0.92 is close to native 1. Now, if you look at the last graph, honestly, I cannot say if the points are going up or going down. So in this case, we cannot tell if it's going up and down, and that's the reason why we use the name no correlation. And it happened that R for this graph is 0.04. 0.04 is almost at 0. Very, very close to 0. In other words, there is no correlation. So I want to go back with you to this example that we did earlier. And actually, remember this, native 0.164. And this is for this problem. Now, for studying for the test. Here's for studying for the test. Here's the 0. And the R we got, let me go back and here remind you. The R we get is native 0.164. So the R we got is native 0.164. Notice that the native 1.64 is very close. It's within very close range of 0. Very, 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 very close to 0. Anything close to 0 tells me there is no correlation. And again, it's not no linear I'm talking about in here. There is no linear correlation in here because it is very close to 0. Now, and that is supports the graph. So the graph in here is supported. Because earlier we said, listen, from the graph we can tell there is no linear correlation, and the picture or the R supports that. So if you want to discuss linear correlation, you need to look at 2 things. You need to look at the graph, and you need to look at R. Both the graph and R will support each other. And this way you can make a better decision. Any questions?
Is there a rule on how close to 0 it has to be for there to be no correlation, or is it just like close to it?
Actually, there is some people say there is a rule. We're not going to discuss that, but anything under 50%, okay, anything at 50 or close to 50 is weak. Anything close to 30%, 20%, whatever, becomes like you go towards the 0, it becomes weaker and weaker. So we have a rule, and we're not going to get into it right now because it's going to add what we cover in this class, but there is a rule, there is a table, actually there is a table in your book called Pearson factor. you can do that, but we're not going to do that. It's going to be an obvious thing when we offer you problems most of the time. It's like going to be like 0.8 is strong, 0.6 it is maybe moderate, 0.5, 0.4 it is weak, 0.3, 0.2 it is very weak, 0.1 no correlation, 0 no correlation. And the same thing with the natives. So the natives, like native 0.9 is going to be strong, native 0.7 will be moderate, native 0.5 will be weak, native 0.1 will be no correlation. You understand what I'm saying? So again, here's a line, here's a 0. Anything within a small range of 0 is no correlation. Now here's the 1. Now as you travel towards the 1, it's going to get stronger and stronger. Same thing in here. It's going to get stronger towards the native 1. So remember, to go from weak, you're going to go through from no correlation, you're going to go through weak, then moderate, then strong, then stronger, and so on. Okay, so same thing the other way around. Okay,
Thank you.
you're welcome. Now, I'm not going to talk about testing hypothesis now because I'm going to add that to the next lecture. So now I'm just going to go in here and try to show you another concept I'm going to talk about, which is how can we use this information to achieve benefits for us down the road. And what I'm trying to achieve in here, by the way, one of the things we can do is really testing claims. And we're going to do testing claims in the next video. But in here, what if somebody says, let me maybe present a problem from your homework. Let's see if I can go to your homework here and get a problem. Uh-oh. Okay. Maybe number 10. Yes. Yes. Here's a problem. Oops. Here's a problem. If you look at this problem here, it says, actually this problem is similar to the one we did before, but this is not talking about exercise, it's talking about hours of study. Now, it says in here, find the equation for the regression line for the given data, then construct a scatter plot of the data. You know what, let me see if I do another one before that. Okay. I want to show you something in here. I did those problems for you and I recorded those already. I'm going to record more, but I'm going to make the screen here smaller. This way I can fit all of those in front of me. Now, if you look at the graphs in here, in this problem here, it talks about, say, the scatter plot below shows the results of 20 randomly selected males aged 24 to 35. So they talk about age in all of those problems as the independent variable, and using age as in this case they call it exponential variable, match each graph with the appropriate description. Now, I'm going to make this large again just because I want you to see this. All of those are age, but look at the y-axis. In the y-axis, the first one, it talks about in thousands of units. In the second one, it talks about units. In the third one, it talks about thousands of units. And the last one talks about units. So let's talk about the first one in here. Here it talks about age and body temperature. Notice that age, all of them age. Look at the y-axis, body temperature. Can the body temperature be in thousands of units? No way. So we're going to look at either 2 or 4 options. Now, the body temperature, like look at the last one. The body temperature tells you it's around 65 to 80. Now, we know that this is not true. Body temperature cannot be between 65 to 80. People will be dead. So in this case, look at this one. It's close to 90 to 100, something like that. So this is the graph. So what we need to do is really just click on this graph and hold the mouse down and drag until you put it into the box. Let me just make this a little bit smaller. This way we can see what we are doing. So we're going to click on this one and drag it down, and and then let it go. So it will be locking in there. Now, what about the second one? Age and balance of a student loan. Leave this alone for a minute. Let's talk about height. Age and height. Yeah, the height it cannot be thousands, the height, but it can be between 65 inches to under 80 inches. So we can drop this box into the one that has the height. Now, for the other two, age and balance on a student loan and age and income. Notice that this is too close to call, but we know that, common sense says that with age, the balance on a student loan is going to come down, because when the older you get, the more you pay, so the balance is going to go down. Wherein here, when it comes to income, with age, people will make more money, because again, let's say you have a job, then within your job you have seniority, you have years of experience, you have many factors that you make more money. So we're going to put the age and income in here. Let me drag it correctly. Okay. And then we're going to take this last graph in there. So this is age and a student loan, because with age, we know that, and let me make this bigger. We expect with age, student loan or balance on your student loan to go down, because you'll be making money on that. So this is how we really drag those down and put them in, because it seems like this is like a game, and a tricky game, but this is the way we do it. So and that's the way it works. Now let me go in here to this example. Now, what is R? We said R is the correlation coefficient. R is a number that measures the strength of a relationship. Okay? So usually any relationship should have two. And actually in statistics we can have more than two, but two. Like in this case, they said take row 1 or row 2 and try to work with and show us if there is a relationship between those two. So I'm gonna try to minimize this screen. Okay. So I'm gonna open StatCrunch in here and open the homework in there. Okay, so and maybe I don't need this StatCrunch, it's gonna open automatically. So here's what we have. We have row 1 and row 2, and we have data in row 1 and row 2. We don't know what the data is all about. This could be age, and this could be blood pressure, it could be anything. Okay, so we want to measure the R, how strong the relationship in here between row 1 and row 2. Do we have a positive relationship? Do we have a weak relationship? Do we have no relationship whatsoever? So we can do that. And look at this carefully in here. Let me open this. I click on this and open into StatCrunch. And it already copied the data into StatCrunch. I don't have to go through this, but let's read this carefully. It says in here, letting row 1 represent the X variable and row 2 represent the Y variable. So when you go to StatCrunch, okay, when you go to Stat, when you go to Regression, and you go to Linear, for the X variable, choose row 1, and for the Y variable, choose row 2, because they tell you to do that. Then after that, they tell you find the R. So when we find the R, here is our R. It is in that table there. It is 0.27. And they want 3 places. It's going to be 0.279. It's going to be 0.279. Now, I want to ask you for a second in here. Is this really strong or weak? to 0.279. You asked me a question earlier. Is 0.279 strong or weak?
It's weak.
It is weak.
Weak.
You agree, everybody?
Yes.
Now, let me show you the graph. Look how beautiful StatCrunch is. You want to see the scatter plot? You see where the arrow in the bottom there? You can click on the arrow, and it will, forget the red line for a minute. It will show you that this line, if you see that line, if you pay attention to the line is almost flat. Okay? Now, if the line goes flat, there is no relationship whatsoever. The line is almost flat. This tells you, and look at the points, are far away from this line. So the relationship really is very weak. And 0.279 is showing that the relationship is weak. Okay? Now, the second thing I want to do in here is, in the second case, they tell you, listen, calculate the correlation coefficient R, letting row 2 represent the X and row 1 represent the Y. Now, what if we go to stat, to go to regression, to go and symbol linear, and look, I don't want, in the second part, I don't want row 1 to be X, I want row 2 to be X. So the X will be row 2 and the Y will be row 1. You see what I did? I reversed them. Do you see that? Because I was told to reverse them. Now look at R. What is R? R is still the same as 0.279. So what we are learning here is that R is a measure of strength. And if somebody tells you to measure the strength between 1 and 2 or 2 and 1, it's the same idea. So it doesn't matter which one goes under X, which one goes under Y. For R, the answer is the same. So the correlation coefficient is the same, remains unchanged for both. Now, but I want to warn you in here. In this class, we're going to go beyond R. So for R, switching the columns will not make a difference. But if you want to go beyond R to prediction, switching the columns will make a great difference. That is the reason why we have to be careful. Even though in here it says it doesn't make a difference, but still we have to be careful. How do we know which one goes under row 1 or X and which one goes under Y? Always you put the predicted, what you're trying to predict. The dependent always goes under Y. So for example, age and income. Okay, we can predict income from age, but we cannot predict age from income. Hours of study and grade. We can predict the grade from the hours of study because the grade depends on how much you study. So the grade will be the Y. Okay. Weight and hours of exercise. We know that the weight is influenced by how much you work or you do work out. So therefore, the weight of the person will be the Y, and the hours of exercise will be the X. Is that clear? And don't try to reverse those. Now, while I'm here, I want to show you something else. When we did this stuff in here, we came up with, you see what it says row 1 equal to? We came up with an equation. Now, if I go in here and I try to do something about it, I can really write an equation here. Okay? So I can really replace the row 1. Let me just go in here. I can replace row 1 with a Y. So I can say Y equal to 16.957. I can stop here, or 76, let's say, plus 0.186. Let me stop in here. And instead of row 2, I can put X. Now I came up with an equation. We put something like symbol like this one. We call it Y hat to represent, this represents predicted Y. Now, if you look at this equation, and let me just make this 8, just to stick with the rounding that I did at the end. Now, this is an equation. This is a prediction equation. Notice in this equation, one thing is, here's the x. Notice the number in front of x is called in math m, or slope. And the number by itself is called y-intercept. So your equation can be written like this, and somebody can say, listen, I want to write my equation like this. I want to write it as y hat equal, I want to start with the slope first, 0.186x plus 16.958. You can do that, because what you did really is reverse those two things. And because of you have a plus sign, with a plus sign, oops, with a plus sign, you can do that. With a plus sign, you can reverse things around. Still, the slope did not change. The slope is this, and the intercept is that. And notice that you pay also attention to the sign. So the intercept is this. So this is the equation of prediction. Now, we can use the equation of prediction to predict things that we did not include. For example, if I'm working on an equation, let's say that I'm trying to look at homes, and let's say that you go to a real estate agent, say, I'm looking for a home. The agent will tell you which area, which zip code, whatever it is, and you tell them. And the agent will go in there and look at all homes in that neighborhood, in that area, and look at the size of the home in the area and the price it's sold for. And he will look at home 1, home 2, home 3, and so on, and will list the numbers for you. Okay? Then come up with an equation. So the equation the agent will come up with is going to be y hat equal mx plus b. Now, then let's say that you found a home for sale. Now, you know x, you know the size of the home that is listed in there. So for that home with that many square feet, can you predict the price? And we're going to try to show you that we can do that. And this is really what they do in real life. But in real life, they don't use linear equations. In real life, we don't just rely on two things, the size and the price of the home. Okay? In real life, yes, we can do that, but this becomes a simple equation. But in real life, we rely on the size of the home, the number of bedrooms, the number of bathrooms, then the size of the backyard, the attached garage or no attached garage. There is so pool, no pool, the condition of the home. There is so many factors goes into that. And that is, they come up with an equation to predict that. Another example I want to give you is when you try to go buy your insurance. Now, when you go to buy the insurance for your car, you know, the agent may ask you a couple of questions, but they're going to get lots of information without asking you, like about your driving history, about your probably address or something like that, about your age, about gender, about they take the type of car you want to insure. There is lots of things that will be asked. And by the way, there are people from statistics, they go collect data based on all of what we mentioned from so many drivers. We come up with a prediction equation, and that prediction equation is the cost of your insurance. And the cost of your insurance will depend on so many things. It is an equation, but it's not going to be simple linear equation. It's going to be called multi-regression equation. And they fill in the information based on your situation, and then they tell you what the cost is going to be. So the computer within seconds will tell you what the cost. And that is a cost is based on a prediction, based on, look, we know that it is cheaper to insure a female than a male. How come? Because data showed that based on records and accidents and everything, men tend to be more at fault than women. It is more expensive to insure a younger person than an older person, more to insure a single person than a married person, more to insure somebody living in zip code, let's say A, than zip code B because of theft, because of break-ins, because of whatever the situation is. So this is how they come up with prediction equations, and this is how they decide things. And this is a great chapter, really, because it helps us understand how we pay for things like health insurance, like car insurance, like cost of education, like lots of things based on those formulas that we are talking about. And we pay for homes, for cars. So any questions for me? I'm talking for a long time now. And anybody wants to ask me anything? No,
No question.
that's an old one. Any questions? Any concerns? Because I'm going to stop here
No question.
and I'm going to start with the lecture. After that, I'll start showing you how to come up with the equation and how to use the equation for making predictions. Now, before I stop, I want to mention something. I promised you for an extra credit. So for an extra credit, I decided to do this. Let me go in here and show you what I'm talking about. Can you see my screen, everybody?
Yes.
Okay. So I am gonna go in here. You're not gonna go there. I'm gonna show you in minutes, but let me just recover where I put my information.
Mm-hmm.
Do you see this survey?
Yes.
Okay. I created the survey, and in this survey, some of it is, I'm not really interested in, but just I created the survey just to give you an idea how surveys are. And so it's the first question, what's your gender? It's not a big deal to me in here. And how old are you? And what is your major? Whatever it is. So those are not major things for me, but I created this survey to give you extra credit. And one of the questions on the survey is, what is your official name? So you need to write your name as it shows in Owen's records. And here is the point. I'm not going to put the survey into Pearson. I'm going to send the survey as an external link. So I'm going to send you a link and you can access the link. Okay. And the benefit here is that when you give me your responses, I'm not going to get who is male, female. For example, for number 1, I'm going to only get the summary. How many male, how many female, how many other. It's not going to tell me who said what. And your name's going to come under one. So this is what they call aggregated survey. It's going to tell me the names of the people who did the survey under one column, but it's not going to connect your name with your responses. You understand? So it's not. So for example, there is a question, is rate your expectations of the online portion of the class, above expected, below expected, whatever it is. So what if you tell me it's below expected? I'm not going to be able to tell who said so, because this is going to come and say, is going to tell me 17 students think it's above expected. We're only going to get the summary of the survey. Do you understand this? So I want you to freely do this survey when you get it, and I'll give you a week, let's say, but I want you to freely answer this survey, knowing that the survey is through an external link and it's not going to connect your name to your responses. Is that clear?
Yes, I do have a question regarding that. Can you, did you say you would send the link, or can you show us the steps to go to the extra credit?
Oh, you don't have to worry about that, because what I'll do is, you know how I do with the collaborating? I send you a link, you click on it and you join my class.
Yes.
I'll send a link, you click on it, and it will open the survey. It's not going to be connected to your class, so it's going to be an outside link.
Okay.
You do the survey and you submit it, and that's it. And it's gonna and it's gonna give me like 10 columns, or let's say I have 20 questions. I have 20 columns. In one column is going to give me the names of the people who did the survey. In the second column is going to tell me how many people are male, how many people female, how many other. But it's not going to tell me which one of the students said so and so and so. So it's going to give me summaries only. Okay? But it's going to be It's going to be an external link. I'm going to send you through an email. I'm going to say, do the survey for an extra credit. And you have till this day to do it. And those people who will do it, when I look at that after the due date, the people who did it, I'll know who they are. I'll give them extra credit.
Thank you.
Is that good? You're welcome. Anybody else? Oh, I'm going to stop then. If you have no questions for me, I'm going to stop and enjoy your nice day today. And hopefully we'll finish this on Wednesday, and then you can take the final exam or the last test as early as this weekend if you want to. Okay? Take care.
Okay, thank you.
Thank you. Have a
Okay,
good
bye-bye.
Bye bye.
You too. Bye-bye.